Hello friend, I am Ranjit Kumar. Okay, in this section we will discuss about the subject digital control system, and in this subject we will see these are the contents: basic of digital control system, jet transform, pulse transfer function. This topic I will cover, and in this section first one is basic of digital control system. We will see the basic of digital control system. First, let us see the definition of digital control system, that is a control system that incorporates a digital computer to perform control tasks within its structure. It is known as digital control system. And if I talk about the advantage of digital control system, so it can perform complex computation, and it is more versatile and flexible device, and its processing is of course is very fast because this is digital in nature, and required accuracy can be maintained in the digital control system. And this is input test sensitivity by using digitally coded signal. Okay, so it is very sensitive in case of the digital coded system signal. And after that, the use of digitally coded signal permits the wide application of the digital devices and communication. In the communication, we can use digital signal, and after sampling some analog signal, and then we will just apply means we will get the digital signal after applying sampler. First one, it is analog signal, and after that, when we apply sampler, then I will get the digital signal. Okay, by changing the program, the schedule of the process can be changed. Okay, only the help of changing the program. This actually there are so many means. And for digital control system, we can use MATLAB program, and in the MATLAB we can change the schedule of the process. It should be changed. Okay, after that, complex can be controlled easily. Complex can be controlled easily means any complex computation can be controlled very easily in the digital control system. Okay, decrease the cost of transmission. Okay, that is very good point. In decrease the cost of transmission of the information, because we will send the signal from sender to receiver. After that, time sharing by several system means time required is very less. Required time is very less. After that, signal can be stored for a long time. Of course, we can store the signal for a long time, and after that, we can also transfer this signal for the long distances without any losing the signal information. Okay, reduced sensitivity to signal noise. These are the advantages of digital control system. Okay, now after that, I will discuss about the block diagram of analog control system. This is the block diagram of analog control system. That is, this is input, this is error detector. The function of error detector is detect the error signal which is coming out from the output that is provided by via sensor and input signal. This is error detector, and after that we will get error signal, and that error signal is further sent to the controller. After that plant, we will get the response, that is output. Okay, now this is the block diagram of digital control system. In digital control system, we just add here interface, that is analog to digital converter and digital to analog converter, which is used for analog to digital converter, that is sampler, and for digital to analog converter, that is hold. After proceeding for the plant, and we will get the output, and again it is controlled by the some sensor medium like temperature. It can be temperature, anything else. Okay, and this is input. So again, this is error detector. Here we will get the error signal, and followed by the this path, and we will get the output. So this is the sample data control system, and you can also say the discrete control system. Okay, now we will see what is sampler. Okay, sampler is nothing but convert the analog signal, continuous signal, into digital signal with some time period sampling instant, that is 0t to t. Okay, where t is the sampling period. Here I'm going to show you that f of t is the input signal, and it is followed by the sampler, and we will get some output which is start function. Okay, that is f star t. This is start function. Okay, that is sampled function. We can also say this as a sampled function. Okay, this is sampled function. Now we can see this is the f of t, that is input continuous signal. So let's suppose this is straight line, f of t. This one is f of t, means function f of t, like f of t equals to, let's suppose, t. Okay, and input, this is input signal. When we apply sampler, we will get like this way. Right? Sampler, it sample the signal here, like that is every instant of time, like this. Okay, so we will get the f star t. Okay, this is small del t, and this one is the sampling instant, that is t. Again 2t, 3t, that is t. This one is t. Okay, this one is 2t, this one is 3t, and so on. That is output of the practical sampler. Now we will discuss about ideal sampler. This is the practical sampler. Okay, practical sampler has some thickness. Okay, some amount of thickness of the signal. Now we talk about ideal sampler. Okay, ideal sampler, output of the ideal sampler will provide like a sequence of impulses. This is the impulse signal. Okay, simple delta signal, impulse signal. Okay, we can see here that is impulse signal. The nature of the signal is impulse. Okay, after that we will discuss, I'm discussing, that is sampling process. Okay, first of all, let us see what is sampling process. Sampler may be considered an impulse modulator. Okay, let's suppose this is a impulse modulator, which is followed by the f of t, which is a modulating signal and providing some del t of t, that is input, another input to the impulse modulator impulse signal. And this is a kind of sampler impulse modulator, because this process is sampling process. And here f star t, that is f dot of t, of course this is convolved with del t of t. Okay, f of t as modulating signal, f of t is modulating signal. Yeah, I told you that f of t is modulating signal. And train of unit impulses, uh, that is del t of t, that is train of impulses. Okay, as carrier. As carrier means it has, means like there are so many impulses we consider here. Okay, which is shown in the following figure. Representation of sampling as a impulse modulator. Okay, again this is continuous signal, and after that we apply here sampler. This is whole circuit is sampler, and del of t, this is the, this is our del t, which is impulse trend function. And after that we will get like this one. This is the impulse signal. Okay, this is impulse signal which is multiplied with del t. And you know, like f of t multiplied with del t, just shift the time period, that is t shifted with this t. Let's suppose this is t, then it will become here, let's suppose this is t, so it will become here t. This is 2t, it should be 2t, because f of t convolved with uh, del t of t, so it just become a function, like this is t dash, so it will become like f of t dash. Okay, so f of t dash will followed like he, f dash means t dash is t, so here f of t dash. Clear? Okay, the output of the ideal sampler is a train of weighted impulse, which is shown in the following figure. I already told you this is the train impulse function. Okay, now we will get the, that is sampled output. Okay, sample output, which is f star of t equals to f of t del t of t. Okay, this is convolved with del t of t is convolved with f of t. Where f of del t is nothing but train of pulses, the impulses. So here I'm just spreading this one t as a t plus 2t plus t plus t, that is del t, and again t minus t means some positive part and some negative part. Okay, as you can see here, this is t and this one is minus t and this one is minus 2t and so on. Okay, now uh, we can write in the summation form like n tends to minus infinity to plus infinity del t of n of t. Okay, so now we can substitute del t of t in the f star of t. So it will become f star of t equals to summation of n tends to minus infinity to infinity del t del of t minus n of t. Okay, now as the function is continuous, okay, as the function is continuous, signal that is f of t appears only at the sampling instant, tick, means ki this is convolved with del t of n of t f of t is convolved with this del of t nt, means f of t is convolved with this del t of nt. So the output means when we multiply, then it will become, I'm just explaining this part, when we multiply these two terms, so it will become f of t minus nt, as I told you earlier. Here I told you like how it will convert. Same f of t minus n of t. Okay, so only it will appears when it will appears means it will appears at sampling instant only. Okay, then the same is denoted as, means we can denote it as a n of t, because it will become it will appears only when we provide the sampling instant, like t equals to t, that is 2t, that is 3t, and so on, and 0 also we can consider. So it will become like f star of t equals to summation n tends to minus infinity to infinity f of nt del of t minus nt. Okay, and also we know that the most of the standard time function are 0 for less than t equals to 0. Okay, that is known. So we can write f star of t equals to n equals to 0 to infinity. Just we put here minus infinity because for n t tends to t less than 0, it will become 0. So just I'm adding here the n tends to, means n equals to 0 to infinity. Positive part we are considering here. Only positive part we are considering. So f of nt del of t minus nt. Now we will take the Laplace transform. We will take the Laplace transform of this f star of t, which is equals to n equals to 0 to infinity f of n of t del t minus nt. Now after taking the Laplace transform, so f star of t will become f of s. Okay, after that, this summation will as it is. Then this f of nt, this is the constant function. You can consider it as a constant function, but here t is the variable. So Laplace transform of del of t, Laplace transform of del of t is 1. Okay, and this is the time shifting property. After time shifting, that is minus nt, so it will become e to the power minus s of nt. That is the Laplace transform of this function. Okay, so now we can spread and we can substitute the value of t, that is t started from 0 to t, 2t, 3t, like means t is started like 0, t, 2t, and so on. Okay, now here f star of s is Laplace transform of f of t, as I told you ki f star of t, the Laplace transform of f star of t is f star of s. Okay, Laplace transform of start function, that is f star of t. Now I'm discussing what is sampling theorem. Okay, sampling theorem is nothing but to reconstruct the band limited signal. Okay, to reconstruct the band limited signal from where? From the sampled signal. Okay, so after reconstructing the band limited signal, the sampling frequency of that signal should be greater than or equals to, it should be greater than or equals to twice of the maximum frequency of the baseband signal, that is message signal. It should be greater than or equals to twice of the FM. Here Fs is the sampling frequency and Fm is the maximum frequency present in the signal, that is in the message signal. So now we see here what is the effect of sampling rate. Let's suppose this is our band limited signal, that is x of f, and function with f, reference of means that in x-axis we are considering frequency. So a spectrum of the signal, input signal, that is x of t. Okay, first one we consider here over sampling. Over sampling means frequency, sampling frequency should be greater than twice of fm. Okay, when sampling frequency is greater than twice of fm, then let's suppose this is my input signal. Okay, so first one is like this. After some amount of frequency we will get another spectrum. Okay, so between these two spectrum, that is the empty space, which is known as guard band. Okay, which is known as guard band. This is the spectrum of the sampled signal. Now under sampling we will consider, so that is for fs less than twice of fm, and it will overlap with one another. So we can see clearly here it is overlapped with one another. So where it is overlapped, that places is known as aliasing effect. Means some amount of this and some amount of this signal is overlapped here. So that is known as aliasing effect. So that is the spectrum of the sampled signal. This is the spectrum of the sampled signal with the reference of frequency f, that is x of f. After that, at Nyquist rate, we can call when sampling frequency which is equals to twice of fm, that is Nyquist rate. In Nyquist rate, we will see the perfect sample, perfect sampling. So as you can see here, that is perfect sample. No guard band, no aliasing effect is occurring here. The reference of x with the reference of frequency f. Now we will discuss about holding device. Holding device or holding device converts the sampled signal into continuous signal. It's just opposite of the sampler signal, the sampling device. That is for sampling device convert continuous signal to the digital signal, discrete signal. Now here holding device just reverse of the sampling device, that is it will convert sampled signal to the continuous signal. And it is not perfectly convert, it is approximately reduce the signal applied to the sampler, that is whatever we applied input to the sampler, that much amount of signal we will not get, but approximately we will get that the signal. Okay, so this is the uh, this one I have discussed about the what is sampling means holding device. The simplest holding device converts the sampled signal into one which is constant between two consecutive sampling instant means that is 0 t 2t and so on. Okay, so that the slope of the whole circuit signal, it should be 0, and other word we can say that which is 0 derivative. Slope alternative of the slope is that is a derivative, first order derivation, uh, that is slope. Okay, and we can write slope like the theta, that is m, that is slope, which is dx by dt. Okay, impulse holding device is called zero order hold circuit. Okay, why we called it as a zero order hold circuit? Because this is zeroth order derivative. Okay, so that's why we call it as a zero order hold circuit. Now see, this is hold circuit, and I'm providing here f of t as an input, and we will get the f of t as a output. So this is our original signal, which is provided before the sampler. This is sampled signal. Now we can see this is the reconstructed signal. Okay, this is the sorry, this is the original signal, and this one is the reconstructed signal. As you can see, that is not, but it is approximately. It is showing like this. Okay, that is analog, and which is zero order whole circuit. Okay, we can consider it as a zero order whole circuit. Like this much, it will go. Okay, so this is f of t. We provide followed by the sampler, and after that we lattice whole circuit, then we will get fn of t. Okay, some function which is called as fn of t. Now transfer function of zero order whole circuit. Here we will here I will calculate what is the zero order whole circuit, and we will see the what is the transfer function of zero order whole circuit. So let's suppose this is my delta function, and some instant of time, sampling instant of time like 0 to t, that is 1 del of t1, and we will provide that is input zero order whole circuit output. So when zero order whole circuit, so it will convert as a step input function. As you can see, that is a step input function which is 0 to t with the reference of time t. As the output of zero order whole circuit is a unit step function appearing up to how much? Up to t. So we can write it as a rectangular function. We can write h of t. This is nothing but a unit impulse function, and we can subtract from, like let's suppose this is unit impulse function u of t, and we can subtract this signal by this signal shifted version u of t minus t. When we subtract from this to this, then we will get that this one signal, that is this one part will be cancelled out, so like this. So it will become u of t minus u of t minus t. Understood? So that things I have written here, h of t equals to u of t minus u of t minus t. Okay, after that, taking Laplace transform. So everyone knows that the h of t is become h of s, and the unit impulse is 1 by s minus, this is the time shifted version of unit impulse, that is e to the power minus st by s. Calculate, when we solve this one, then we will get like h of s, that is 1 minus e to the power st divided. This is our basic function for the zero order transfer function for the zero order whole circuit. And we will use in the whole digital control system this as a zero order whole circuit. So this is the definition of the zero order transfer function, that is Laplace transform of output of the zero order whole circuit divided by the means to the ratio of output of zero order whole circuit to the ratio of Laplace transform of input of the zero order whole circuit. Now I am discussing about Z transform. Okay, so these are the standard equation for the Z transform, that is f star of s equals to, no, this is the impulse strength that we are means calculated here. Already we see how that function came here, that the same function I have written here in the Z transform. Okay, from here we will calculate the Z transform. Okay, where t is the sampling interval sequence with followed by the sequence, n is the sequence, that is 0 1 2 dot dot dot, dot n up to n, and s is the Laplace variable. Here s is Laplace variable, that is s equals to sigma plus j omega, that is s equals to sigma plus j omega, which is frequency component. Now we will substitute z equals to e to the power st. So that is s equals to 1 by t log e base z. And also considering a circle, we can say circle, that is the unit circle, and we considering outside of this unit circle region of convergence of this function for z greater than 1. Okay, z is nothing but the equation of this circle. Okay, after solving here from means when we apply logarithm here, then we will get t s equals to 1 by t log e base z. Now substitute this function in that equation, same equation, we will get f star of s, that is s equals to 1 by t log e to the log e base z, that is n equals to 0 to infinity f of n t z to the power minus n. The relation given above is known as z transform. This is nothing but z transform of which function? F of t, and which is denoted by f z transform of f of t. Else we can represent it by like Laplace transform is represented by capital F of S. So same we can represent Z transform as f of z. So therefore f of z complete this function we can write like f of z, which is equals to n tends to 0 to infinity f of n t z to the power minus. Okay, here's some question I have taken on the basis of z transform is how to find out the z transform for the unit impulse function. So here first of all let us consider f of t equals to u of t, that is impulse step input function. So after that just change with t n of t, okay, because this is the sampling instant, so it will become u of nt. Now we know that f of z equals to n tends to 0 to infinity f of nt z to the power minus n. So when we provide f of nt, so we will just substitute the value n equals to from 0 to infinity. So as you can see, this is the unit impulse function. So the value of from 0 to infinity, it will always equals to 1. It will always equals to 1. So directly we can write from in this limit, that is n equals to 0 to infinity, that is z to the power minus n. Now after that, we just expanding this summation, and we can write 1 plus z to the power minus 1 plus z to the power minus 2 as so, which is the standard expansion of of 1 minus z to the power minus 1 minus x. Yeah, you can conclude it as a like 1 plus x square plus x cube as so on, and it will become 1 minus x to the power minus 1. So directly you can compare with this function. So 1 by 1 minus z inverse whole inverse, it will become inverse, that is reciprocal theorem. With the help of reciprocal theorem, that is 1 by x. We can write x to the power minus 1 is as 1 by x. Okay. Now another function, that is ramp function n u of n. Again we will convert n of t. So u of n, let f of nt, that is first this one function I have considered f of nt, and never confuse with that we use n of t, and here I'm using only n. Okay, no need to confuse, because the Laplace transform, whenever you will get the take the Laplace transform, you will get directly 1 divided by s of unit step function. The Laplace transform is always 1 by s, so don't worry. Just keep this in mind. N of t, though it here it is present t or not, you will get the same value. After taking z transform, we will get z divided z minus 1. As you can solve this one, you will get this function. So here 1 minus z inverse. Okay, after solving this, so that is 1 minus 1 by z, 1 divided by this one, that is z minus 1 by z. After that, suffering this one, z divided by z minus. This is the z transform of the unit step function. Okay, after that, now we multiplying here n, that is ramp function. So that is the with the properties of the z transform. Whenever we multiply time function in the means multiply the time function in input side, then in for output side of the z transform, we have to use the derivation, means differentiation of the z transform of this input function. So followed by the minus z d by dz f of z, okay, equal, which is equals to minus z d by z, z divided by z minus 1, because f of z is from here. I am just substituting the value. After solving this, we will get Zn of u of n, that is equals to Z divided by Z minus 1 whole square. And when you say that how to solve this one, just see minus Z is Sn. Now dy by g, that is d by dz. Let's suppose d by dx, okay, for solving. And that is what I can say, u by v, no? U by v. So everyone knows that d by dx. First, we will take this reference, means first one, and derivate this one function, and after that keep it outside and derivate below one and the square of the below one function. Okay, square of the below one function. So after solving this, you will get z divided by z minus 1. So the z transform of n u of n is z divided by n minus 1. So in a single word, I can summarize in digital control system, and in the basic, we see the definition, some advantage. After that, basic block diagram, analog, what is the difference between analog and digital. After that, sampler, some function of the sampler, ideal sampler, some process, some theorem regarding the about the sampling theorem. Means after that, we see the effect of the sampling. Then we studied about hold circuit, holding device, which is nothing but a type of what I can say, from digital to analog converter, digital to continuous converter, discrete to continuous. After that, we learn from about Z transform, is from a Laplace transform. How I will get the Z transform, I have explained very well. Okay, so after that, I will attach this PDF in the description. Okay, you can download it. Yeah, bye bye.